talk is on abstract value iteration for hierarchical RL, and this was published in AI Stats 2021, so it's quite recent. Um, let me start with a quick introduction to hierarchical RL. Um, let us start with an motivating example where there is a maze of rooms and there's a robot that is trying to navigate this maze of rooms. Let's say periodically you could observe the state of the robot, which is simply the position in R2. And let's say you can control the robot by giving it velocity commands. And our goal is to learn a policy to go from the blue region to the green region. And we a priori do not know which rooms have a doorway between them and which rooms do not. So this is something that you have to figure out by exploring in the environment. And if you try to use regular state-of-the-art deep RL algorithms for this problem, they usually do not work because firstly, this is a large state space to explore. And secondly, most algorithms will give you a solution in which the robot will go to the room in the top right corner from which it cannot really make any progress. And hierarchical RL is supposed to work in such scenarios where there is this long horizon task and it requires a lot of exploration. The idea behind hierarchical RL is typically you have a hierarchy of policies. For simplicity, let's say um, there are two levels of policies. A high level policy pi h, which maps the current state to the next intermediate goal, say S prime. And there's a low level policy that takes the current state S and S prime and outputs a concrete action, right? And the high level policy is only invoked every few steps so that the horizon at the high level is reduced effectively. And this works in many cases because it decomposes the problem into two simpler RL problems, and there's also better exploration at the high level. But unfortunately, for this particular example and many examples where you really have to plan at the high level, it doesn't quite work. And if you apply existing deep RL, hierarchical RL algorithms, they tend to go to the same local optimum. So the idea behind our work is that many environments, including this one, have a lot of structure in them, and you might know that this structure exists a priori, and you want to use the structure in the environment in order to explore better, right? So this structure is encoded in the form of abstract states. So an abstract state is simply a subset of the state space. And there's also an abstract graph. For example, in this setting, each room might be an abstract state of its own. And you might know beforehand that there are these rooms. And abstract graph simply is a graph with abstract states as vertices, and edges denote what high level actions you want to consider. For example, in this setting, there is an edge between 7 and 8, although there is no doorway between them because you don't know that there is no doorway between them. But nonetheless, you know that they are probably next to each other, right? Um, Now, suppose this sort of information is available to you beforehand, then the high-level idea is simple. First, you learn one policy for each edge in the abstract graph that takes the system from any state in the source abstract state to some state in the target abstract state. And once you learn these policies, you sort of figure out what policies to use and how to combine them using a high-level planner, right? So the main questions that we answer in this paper are how to plan using the learned policies, as well as under what conditions on these abstract states can we guarantee something about the final learned policy. Before moving on, I'd like to give a brief introduction to options. Options framework is popular in RL for representing these high-level actions, right? In our case, high-level actions are these policies that take you between rooms, let's say. So an option is simply an extended action where it's represented as a tuple, pi, comma, I, comma, beta, where pi is simply a policy and I is a set of states from which you can start using this option. And beta maps every state to the probability that the option terminates in that state. So when you execute this option, uh, the policy pi will be used until you terminate, right? At which point you will be required to choose another option. And let's say you have an MDP where you also have trained these options, uh, these high-level actions, and you would like to find the policy that is best with respect to these options, right? You want to find a high-level policy that maps every state to an option that is best with respect to the rewards, with respect to discounted sum reward, right? And this can be done using value iteration as shown in prior work. We just have to define the transition probabilities and the rewards appropriately. For example, the reward of taking an option O at state S is simply the expected discounted sum reward until the option terminates. And the transition probabilities are not essentially probabilities; they are time discounted. So the probability of going to state S prime when taking option O from state S is simply sum over all times gamma raised to t, which is a discount factor, multiplied by the probability that the option terminates in state S prime, given that it terminates after exactly t steps, and multiply by the probability that the option terminates after exactly t steps, right? Once you define this, you can define these Bellman equations, which look very similar to regular value iteration. Um, so all you need to do is find a fixed point of fixed point solution to these equations. And in the end, the optimal option policy or high-level policy is simply one that takes that maps a state to the option that maximizes this Q value, Q of S comma O, which is defined by these equations. Uh, this is all good. So for now, so in our framework, we have options for every edge. So um, for every edge, we have this tuple where pi is trained to take the system from S tilde to S tilde prime. And the initial set is simply S tilde. And beta is given by you terminate if you end up in a state that is in any other abstract state except S tilde and zero otherwise, right? You terminate as soon as you reach some other abstract state. And in order to compute a high-level plan, we can simply use value iteration. Uh, but in the case of continuous state spaces, performing value iteration might involve function approximators. But rather, we would want to do value iteration or planning just on the abstract state space, right? So in order to do that, we define these analogs of transition probabilities and rewards for the abstract setting, right? And we have two sets of such quantities, the one denoting infimum and one denoting a supremum. So let me quickly go over the infimum definitions. So the transition probability of going from S tilde to S tilde prime on taking option O is simply infimum over all states in S tilde of the discounted time discounted transition probability that option O terminates in the abstract state S tilde prime when it's taken at state S. And the R tilde inf of S tilde and an option O is simply the infimum over all states in the abstract state S tilde of the expected discounted sum reward of the option O when started in state S. right? And supremums are defined appropriately. Now you can define, you can take the same equations, the same Bellman equations that you had, except that replace the state space with the abstract state space. And you have one set of equations for inf and one for supremum. And you will end up computing two sets of values, vinf and vsup, for each abstract state. And what do these values give us, right? We want to analyze what these values give us. And can we do anything with just this information, right? So in order to do that, we first define these errors, epsilon t and epsilon r. Epsilon t is nothing but the worst case error between t sup and t inf. And epsilon r is similarly the worst case error between the rewards supremum and infimum. And what we can show is that this procedure, like the Bellman equations, are in fact contractions, and hence our procedure, which we call robust abstract value iteration, converges if epsilon t is small enough, if the error in transition probabilities is small enough. And we also have that the true best value of a state S is contained between this infimum and supremum values of its corresponding abstract state. And furthermore, if we choose the high level policy to simply pick the option that maximizes q star inf, uh, then we can obtain some bounds on the suboptimality of this high level policy compared to the best high level policy, which is rho star, right? So uh, and I want to point out, for those familiar with abstract interpretation, what we are essentially doing is um, performing abstract interpretation over value iteration, where the abstract domain is simply the interval domain. Right? And so that's good. And what we get from the theory is that you want abstract states where every state within an abstract state is similar in terms of transitions and rewards in order for this to work. And now the theory actually doesn't assume that the abstract states cover the state space. So they are more like subgoal regions rather than abstract states. So for example, there are two choices here of abstract states, where the first one denotes uh, each abstract state being a small region in the center of each room. And the second one denotes an abstract state being the doorway regions. And these tend to work better because they are sort of smaller, and probably the states within them are similar, right? And the second choice is a bit special because they form what are known as bottlenecks. So any policy that takes you from 3 to 9, the blue region to the green region, has to go through some of these abstract states. And in that case, in that special case, we have some stronger guarantees, but it might be hard to know a priori what these bottleneck states are. So it's not really necessary to have them to be bottlenecks, but you get stronger guarantees if they are. So now, how do we train options, right? How do we train these transitions that take you between different abstract states? We use standard reinforcement learning, and these are potentially shorter horizon problems that are simpler than the whole problem, and it's probably easier to train. But there is a small issue here, which is that uh, you are the planning algorithm requires that the options that you train work well for all states, equally well for all states in any given abstract state, right? For example, in this abstract state one, let's say that you're looking at a state, a position in the middle of the doorway. It is much easier to construct a policy that reaches 4 as opposed to some state in the corner of the doorway, right? Which requires a lot more maneuvering. And training a policy that works well in the worst case uh, might be hard, and it might require a lot of samples. So, but what we can, what we really want is the option to work well on the states that you actually reach. For example, when you're taking the abstract edge from 3 to 1, if you could only um, train on the states reached when you are taking this policy, uh, that is good enough, right? So we use this observation to propose uh, a hierarchical RL algorithm that we call alternating abstract value iteration, or A-AVI. So what we do in alternating abstract value iteration is we maintain a distribution uh, for every abstract state. We maintain a distribution over concrete states in the abstract state, and we iteratively do a few things. First, we use these distributions to learn policies or options that take you between different abstract states, and then we estimate the transition probability rewards for those options and compute a higher level plan using our abstract value iteration procedure. And once we compute a plan, we execute this plan and see what states are reached and use these states to update these distributions. And we keep repeating until for a fixed number of iterations. And you can also show that this converges under some no regret assumptions, but I will not go into the detail here. Um, so what we do, we actually evaluate this hierarchical RL algorithm on a bunch of environments. The first set of environments are these rooms environments where you simply control the velocity of the robot. And we also consider more challenging environments, which are these maze-like environments where the robot is actually not so simple. It is the Mujoko ant, which sort of is slightly harder to control. And what we show is that we can learn better policies with fewer samples, right? Here, the plots indicate learning curves where x-axis is the number of samples and y-axis is the probability of reaching the goal. And the blue line denotes our approach, and we compare against many state-of-the-art hierarchical RL algorithms, and the blue line denotes the same approach without alternation, right? It is essentially learning all options once and tries to plan. And as noted earlier, it requires a lot more samples to learn because it needs to learn these robust policies for transitions. And we also have a study on comparing different sets of abstract states for the room's environment. The doorways, which are the bottleneck set of abstract states, seems to perform the best, followed by the centers of the rooms, and finally the case where you consider the entire rooms as abstract states, the sandbox over. Here, the y-axis denotes the discounted reward, so it's higher when you reach the goal faster. But if you actually look at the probabilities, it's they roughly converge to 1 for both room centers and doorways. So uh, yeah, so in certain cases, it's fine if the abstract states are not bottlenecks. And uh, our approach still requires an expert to give you this additional information, and we sort of experimented with what we can do to eliminate this assumption. And we have some studies on using randomly generated abstract states, where we randomly pick a bunch of points and then consider small regions around them as abstract states. And then we run our we run our algorithms on these, and we still can show that we can learn reasonably good policies. Um, So to conclude, we propose two algorithms. One is a planning algorithm, which has theoretical bounds on suboptimality. And we propose a practical hierarchical RL algorithm that works quite well in practice. And some future work includes this generation of good abstract states, maybe from specification languages or just from rewards by exploring. And and also many of these options might be doing similar things to each other. So it might be good to work on ways to identify these different options that are similar and try to share policies across them in order to improve sample efficiency. Um, that's it for my talk. Thank you for listening, and thanks for inviting me to give a talk here. And if there is time, I would be happy to take questions.
Thank you very much. Are there questions? So if you have a question, you can simply unmute yourself and ask, or you can write in the chat. So maybe I can start with a very simple question. So if I just think of the non-probabilistic reactive synthesis setting, does this give you a way of doing abstract reactive synthesis, right? Where you kind of learn strategies for, some particular things, and then you put them together in a way. So, you're working in the world of Markov decision processes, but does this imply something about hierarchical reactive synthesis?
I mean, the theory does hold. Yeah, I mean, in the pure automata world, the theory would still go through, right? I mean, it does, like any fixed deterministic process is also an MDP. But I think what this is essentially saying is if you could identify sort of key points that you want to visit during your execution, then that is good enough, and you have some sort of you can abstract away the problem into a much smaller, simpler finite state problems, even if your underlying thing is continuous. But if your underlying thing is finite, even I think you can still do this. If the state space is large, you might want to reduce it to a smaller state space by doing this sort of approach. But that setting is not something that we studied, and yeah, maybe it's a good direction for future work.
Thank you. Other questions? So if I may just ask a follow-up. So these abstract states are, so you said that at this point you kind of, so the user has to provide them?
Yeah.
But in your experiments, you just tried some random points as intermediate abstract points. Is that right?
Not in the primary experiments, but we also considered randomly generating rooms environments.
I see. So in the primary experiments, essentially the structure of the problem, the rooms, already gave you a natural mapping to abstract states.
Correct. Yeah. And in this case of Ant, we sort of know what the environment looks like. So we just pick a bunch of points in certain key areas and use those. Yeah.
I see. Very good. Are there any other questions? If not, let me thank Kishor again on behalf of all the organizers and the attendees for the seminar. And this brings us to the end of the seminar series. Thank you everyone for coming, and thank you to all the speakers for coming and giving a talk here. Okay, that's it. And have a good rest of the evening. Thanks.
Bye.
Bye.